Okay, let's go ahead and get started. So today we're going to talk about the last topic in this section on exponential growth and logarithms. Um, Today we're going to be talking about modeling things using exponential functions. This is actually a pretty large topic in general. There's a lot of different ways of modeling using exponential functions. For example, a lot of different statistical models in the real world will be fitted to exponential curves. We're not going to discuss using exponential curve fitting tools to try and model in a more sophisticated way. That's something that you will see if you take a statistics class. Um, but uh, we are still going to talk about the basic idea of using a exponential model um, to model things. And so the other type of modeling we've done in this class so far is linear modeling. And exponential modeling is kind of similar to linear modeling. So in a linear model, we had y is equal to mx plus b, where m was a slope or some constant related to the rate of change. It is in a linear model. M is actually the rate of change. It's not just related to it. It's straight up the rate of change. Um, and B was your y-intercept, right? Or the initial quantity or initial position or amount. Exponential models are similar. An exponential model is typically y is equal to c times e to the kt, or kx if you prefer. Um, we sometimes use t instead because exponential models are so often they so often use time as the independent variable. Okay, but this C and this K are exactly similar to the things we have over here. This C is an initial amount or a y-intercept. And this K is some constant related to the rate of change. Unfortunately, it's not quite as straightforward to find C and K. Well, C is just as straightforward as B is. It's the initial amount you're given. And you'll almost always be given this initial amount, right? K is a little bit trickier. We're going to have to use some of the things we've learned in this unit so far. We're going to have to use some logarithms to figure out what K is in general. Um, so before we get into solving for this K, a quick note about exponential models and the K value in general. So note y equals ce to the kt, and a of t equals pe to the rt are the same model. Okay. exponential growth and decay and continuously compounding interest are the exact same model. We just see them with different letters. Okay, and in fact, going further than that, sometimes you even see y is equal to y naught e to the kt instead, just to confuse everyone even further. That y naught, whenever you have like a variable and then like a zero below it, usually that means like an initial quantity of that, so that y naught stands for the initial y amount. I like CE to the KT. It's the form that you will most commonly find when solving when actually running into these naturally in mathematics. I will refer to PE to the RT when we're talking about compound interest, and CE to the KT in every other situation. But these are not two separate formulas. They're the exact same formula, okay? For continuously compounding interest, that P is your principal amount. It's the initial amount that you started with in your account, right? And that R is your APR as a decimal. It's some constant related to the rate of change. Okay. A second note, if K is greater than 0, then y equals CE to the KT represents exponential growth. So we get one of these functions looking just like a exponential function. Okay, it starts at a certain point and then it's going to go up, and eventually it's going to grow quickly without bound. Okay. If k is less than 0, then y equals CE to the KT represents exponential decay. And exponential decay looks like exponential growth, just flipped horizontally, right? Because by making k negative, what we're doing is we're applying a horizontal flip, all right? So that means that it's going to go closer and closer and closer to 0. We will see both types of models in this class, both exponential growth and exponential decay. Okay. And then one more note, note number 3. Nothing in the universe is truly exponential. This is more or less a paraphrase of a quote from Carl Sagan. He was a pretty strong proponent of this concept that nothing in the universe can possibly be truly exponential. If things in the universe were truly exponential, then that would mean that eventually they would grow without bound, and exponential growth gets incredibly large eventually, always. Okay, so at some point all exponential models break down. Okay, um we'll take a look at why, like how and why, and what this looks like when we start looking at some examples. But just know that, for example, exponential decay says that if you're using an exponential decay model to model the amount of Tylenol left in your bloodstream after you take some Tylenol for a headache, the exponential decay model is going to say that there will never, ever again, after you've taken that Tylenol, be no Tylenol left in your system. But the reality of biology is that eventually your system flushes out every single trace of that Tylenol. Okay? That one we can kind of sidestep by noting that the things in the universe are actually not a continuous number. There is a smallest possible amount of Tylenol. There is one molecule of Tylenol, right? And if your exponential growth or decay equation says that you would have less than that amount left in your bloodstream, then clearly you should have 0 at that point. But Nevertheless, exponential decay says that you would never, ever, ever again have no Tylenol in your system. And similarly, exponential growth will say ludicrous things like in the year 2055, the population of, or 2,500, the population of the United States will be um, more humans than you could possibly fit on the globe. So, um, we will talk in just a bit about a way of getting around that idea. So let's take a quick look at an example of an exponential modeling, something that we can model using exponential growth, and talk a little bit about the limitations of that system. And then we'll look at some other examples, and then we'll talk about logistic models. So, example. In 1970, the population of the USA was 203.9 million. By 1980, the population of the US had grown to 227.2 million. Let's make a model. So make an exponential growth model for the population of the United States in year T, where T is years after 1970. So this type of phrasing here, where we're making a model in terms of T, where T is years since blank, is something that shows up pretty frequently. We don't want to actually put the year in as our T value, otherwise we're going to end up with a really funky looking exponential growth curve. And also that doesn't make sense either, because in the year 150, the United States of America was not a country, right? There were people living in what is now the United States of America, but they definitely were not part of the United States as a country as it currently is, the way we think about it. And there's no reason to believe that the relations there should necessarily relate to what the United States was doing in 1970. Okay, so you're always going to have some sort of limited window where your model makes sense, and a lot of that is sort of thinking about common sense, like what should I be, how far out do I think this data even makes sense. Okay. And again, there are generally more sophisticated ways to model these types of things that people use in real world situations. This is sort of just a taste. So, another quick note about exponential growth models is that, much like linear models, another similarity is that if you have any 2 points, you can make a line, right? And it's a unique line. The same thing is true for exponential population, or for exponential growth models and exponential decay models. If you have 2 points, there's a unique exponential model that fits those 2 points. Okay, so we can use these 2 points to figure out what that model should actually be. We know our model is going to be P of T for population is equal to CE to the KT. Okay. And first, we have 2 points. The point from the year 1970 is going to be the point 0, 203.9. This is from 1970. And the point from 1980 is going to be 10, 227.2. Note that in 1970 our t-value was 0, and in 1980 our t-value was 10. This is because t is measured in years since 1970. So the independent variable quantities, the t-values, are not 1970 and 1980. They are 0 and 10. Okay. We can use our first point to figure out one of our two unknowns. We do not know what c is. We do not know what k is. So we know that p of 0 is equal to 203.9. Because if we plug in 0, we should get the y-coordinate of the point along our curve, right? And this is also equal to ce to the k times 0. But k times 0, it doesn't matter what k is. K times 0 is 0, right? So this is ce to the 0. And e to the 0, just like basically everything else when we raise it to the power of 0, is just 1. So c is equal to 203.9. You can skip this very first step of plugging in if you remember. When I mentioned the exponential model in the first place, this y equals ce to the k x kt whatever, that c is the initial amount. In this situation, since t is years since 1970, the initial amount would be the population of the United States in 1970, which is 203.9. So just by the definition of what C is, you could have just plugged in 203.9 if you wanted to. I'm not going to take off any points if you don't show me the work for finding C value, if you just know it's the initial amount. Okay. However, the next part, we are going to actually have to do a little bit of math. We are going to have to use some logarithms. All right. So P, we're going to plug in our other point. P of 10 is equal to 227.2, which is also, we know that C is 203.9 times e to the k times 10, right? Because we're plugging in 10 for t. That's what this P of 10 says, right? So now what we have is we have an exponential equation here that we can solve for k. So let's go ahead and do that. In order to solve for k here, the first thing we should do is we should isolate this exponential term. So let's divide both sides by 203.9. So we get 227.2 over 203.9 is equal to e to the 10k. All right. If you want, you can simplify this 227.2 over 203.9 and just give a decimal there instead. Like you can plug it into your calculator. I'm going to leave it as a fraction, just so that we don't have to, just so that we get an exact answer, or a closer to exact answer at the end with less rounding. Okay, we're going to have to round eventually. The k value is going to be, the k values we get tend to be really funky looking. So at this point, we have some number is equal to e to the power of something. So we can either apply a natural log to both sides, or we can just rewrite this as a logarithmic expression. I prefer to think of it as applying a natural log to both sides. On the left-hand side, that's going to give us just ln of 227.2 over 203.9. And on the right side, the ln and the e basically cancel, right? So we just end up with 10k. And now all we need to do to find k is we just have to divide both sides by 10. K is equal to the natural log of 227.2 over 203.9, all divided by 10. So let's go ahead and plug that in real fast. So that's the natural log of 227.2 divided by 203.9, all divided by 10. And we get our k value of approximately 0.0108. All right. For these ones, generally what I'll do is I'll keep 2 or 3 significant digits. What that means is that basically the first 3 non-zero digits I'll keep. In this case, that means that I'm taking 4 digits because the first thing after a decimal was a 0. Right. Um, I probably wouldn't be that upset if you picked 0.011 for this problem, but generally I try to keep 3 significant digits. So now we have our model. We know what K is, we know what C is. So our model for the population of the USA is P of T is equal to 203.9 times e to the 0.0108 k. Once we've found our exponential model, we might want to do some stuff with it, right? So, for example, let's for let's say B, let's use our model to predict the population of the USA in 2000. Okay. So in this situation, we're going to plug something into this. The temptation is to plug in 2000, but we can't do that. Our model is not in T, the year AD or B or CE or whatever. It is in terms of years since 1970. Okay, so what we're plugging into our population function is not 2000. We are in fact plugging in 30. Okay, and let's go ahead and do that. So that'll be 203.9 times e to the 0.0108 times 30. And let's go ahead and punch that into our calculator. And our calculator gives us approximately 281.9 million as our population. Incidentally, this model is in millions, by the way. Which the actual population of the United States in uh, 2000 was 282.2 million. So that's not too bad. For this relatively close date, right? Our model was based on dates in 1970 and 1980. So for this relatively close period of time in 2000, just a little bit outside of that, this model is actually pretty accurate. And the USA between the years of 1970 and 2000, 2010, so on, we've been experiencing pretty much straight up exponential growth. The United States doesn't really have a ton of limiting factors on its growth right now. It's a very, very large country. There's a lot of natural resources. There's nothing that's sort of cramping us and causing us to have some sort of population cap or anything that's sort of limiting the growth of the United States right now. It's a relatively quickly growing population, or at least a relatively exponentially growing population, I should say. Um, so for part C, let's use our model to predict the population of the US in 3970. This serves 2 points, okay? Not only is it going to show how ludicrously bad our exponential growth function is for things that are way outside of the realm of what makes sense, it's also going to show you what happens if you plug in 2000 instead of 30 to your exponential growth model, okay? So 3970 is 2000 years after 1970. So this would be P of 2000. And P of 2000 is going to be 203.9 times e to the 0.0108 times 2000. Let's go ahead and plug that into our calculator. That's 203.9 e to the power of 0.0108 times 2000. And we get that number over there. We get the population is 4.899 times 10 to the 11. Okay. In other words, that is about 4.8 or 4,000 or 4,899 5, 6, 7, 9, 10, 11. It's about 489 trillion 900 billion millions. So we can throw 6 more zeros on that for the actual number of people. All right. That's people. All right. That's 489, I think, quintillion 900 quadrillion people. This is insane. Okay. There's no possible way that our population should be that large. Okay. That is literally if you took people and you stack them side by side, all laying next to each other, and you stack them on top of each other all across the entire surface of the United States, okay, and then you stack them up to the edge of space on top of each other, like logs, that would not even fit in the footprint of the United States. Okay, this number is colossally large. It is insane. All right, there is no way that you should look at this number and say that this is an appropriate number of people in the year 2000, right? Because it's very obvious that we don't have a number of this size. All right, so something that you can be doing while you're using these exponential models, if you input something that's wrong, you're probably going to get an answer that's way off. All right. So try to use a little bit of just, I hate to use the word common sense because math is not common sense in general. It's facetious of me to say that things in math are common sense. However, I do think that there should be a little bit of thought, like just looking at your answer and checking it and say, does this make sense at all? Is this something that could really be happening? Or is this some sort of crazy thing? Okay. And when Carl Sagan says that exponential models always break down, there's no such thing as true exponential growth in the universe, this is what he means, right? This model is clearly not accurate for the year 3970, okay? If there is one thing I can guarantee in life, and of course I'll never be able to follow up on this because none of us are going to be alive in the year 3970, but I can guarantee you with 100% reality that the number of people in the United States in the year 3970 will be nowhere close to this number. Okay, it will not even be in the same ballpark. It might be a very large number, but it will not be this large. Okay, so there are limits to what exponential growth models allow you to do, and generally they're only accurate for numbers that are pretty close to where you generated your model. Okay. In statistics, when they use exponential models, they're typically using it to predict data points that lie inside the data range that they've gathered data on already. Okay, so population growth, for example, is not a fantastic example of somewhere that you would be using exponential curve fitting, but some relations and especially in like biology, do follow these exponential growth models. So, all right. So one more quick thing that we could do with this model, part D, using our model, let's predict when the population of the US will pass 300 million. So this is actually something a little bit different from predicting the population in a specific year. Instead of asking us to plug in a number, this is asking us to set it equal to a number. Okay, so for here, what we're saying is we want P of t to be equal to 300. In other words, we want 300 to be equal to 203.9 e to the 0.0108 t. Okay, and we need to solve for t. And this is almost exactly the same process that we used to solve for k in the first place. Okay, we're going to isolate the exponential part by dividing by 203.9. So 300 over 203.9 is equal to e to the 0.0108 t. And then we'll apply a natural log to both sides. So ln of 300 divided by 203.9 is equal to ln of e to the stuff, but that's the ln and the e will cancel, and we'll just get 0.0108 t. And from there, we just need to divide both sides by 0.0108 to get that ln of 300 over 203.9 is equal to 0.0108, or divided by 0.0108 is equal to t. And let's go ahead and plug that into our calculator real quick. That's ln of 300 divided by 203.9, all divided by 0.0108. And that gives us about 35.75. Okay. So this is sometime in maybe around September of 2005. So the population of the United States passes 300 million. We're going to call it in 2006 then, because the population stated for 2005 will be smaller than 300 million. The population stated for 2006 will be more than 300 million. So passes 300 million in 2006. So for what it's worth, it's possible to sort of guess and check your way through this problem, to start just plugging in like, oh, let's plug in, well, it's going to be after 30, so let's plug in 31, and then 32, and then 33, and then 34, and then 35, and then 36. While that does technically get you to the correct answer, that'll get you to 36, or 2006 as your correct year. You will not get full credit for that. You'll get some credit because you got to the answer, and, you know, that's good to demonstrate that you can still get there. But in order to get full credit, you should use the logarithms that we've used in this unit to actually correctly solve this equation. Okay. All right. So in reality, we passed 300 million in 2007. So this is pretty close. Okay. So that was a bunch of different stuff with a single exponential growth example. Um, Essentially, what we did is we made our exponential growth model, and then we answered a handful of questions surrounding it. I like questions like this a lot, and it's definitely the type of question that you can expect to see on an exam. So yeah, it's fun to do nice little population growth exercises with real world populations. So, does anybody have any questions so far about either the example or the stuff I talked about at the beginning of class? All right, let's move into um, what's called logistic growth. Okay. So logistic growth is kind of like exponential growth, but it accounts for one of the big downfalls of exponential growth models. Um, in particular, it accounts for the fact that uh, growth in the real world is always capped. Like there's always going to be some cap on a population. Okay, so logistic growth um, considers what's called carrying capacity, um, or a cap on exponential growth. So, for instance, it's clearly insane that the population of the United States would ever reach that 489 quintillion mark, right? Like that would never, ever, ever happen. That's too many human beings, right? However, it is possible that what happens is that eventually there's a certain amount of resources that will cause a population to stagnate and sort of stay at a specific amount. Okay, if you introduce a bunch of fish into a pond, those fish will populate the pond, assuming that it's a good environment for them. They'll populate the pond to a certain point, but eventually they're going to really reach some kind of equilibrium, right? Where the population no longer grows. So, what's going to happen is that you're going to have exponential growth at first, right? So you'll see that spike of population when that population is unbounded. Maybe there's no natural predators or not enough natural predators, or there's just enough resources that everybody survives at a high rate or something like that. But eventually, once that population grows enough and the population starts to run out of resources, the growth model will sort of tail off. Okay. And logistic growth um, has sort of this horizontal asymptote at the carrying capacity. So the formula for logistic growth is a lot more complicated than the formula for exponential growth. I am not going to ask you to develop logistic growth models on your own because it's frankly unrealistic and you'd have to be able to do differential equations for that. So no, 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 no. However, I am going to ask you to interpret logistic growth models. So the formula for a logistic growth model is P of t is equal to C over 1 plus AE to the negative BT. Okay. Where C is equal to the carrying capacity of the population. And C over 1 plus A is equal to the initial population. And um, B is a constant related to the growth of the population. I can't be much more specific about B than I am right here. You genuinely do have to solve a differential equation in order to figure out what B should be, which is way, 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 way so far beyond the scope of this class that I'm not even going to talk more about it. However, the other two things are things that you should be able to identify, right? And given a logistic growth model, that C over 1 plus A part, that's not even that important because given a logistic growth model, if you want to find the initial population, you can just plug in T equals 0 anyways, and that's going to give you exactly C over 1 plus A. So it's not that big of a deal. The important part is to know that that C, whatever number is on top of your logistic growth model, that's what the assumed carrying capacity of the population is. Okay. So a relatively good example where we can use a logistic growth population or model for a population is actually the population of Japan. Um, so a logistic model for the population of Japan in years since 1960 is P of T is equal to 130 population of Japan in millions T years since 1960 is 130 over 1 plus 0.392 e to the negative 0.044 t. Okay. So basically, what this is saying is that there's essentially sort of a carrying capacity limit on the population of Japan of about 130 million. And that seems to be true, actually. Over the past 20 or 25 years, the population of Japan has been basically stable right around 130 million people. Japan is a pretty small island. It's not a very large place, especially compared to a country like the United States. And in that relatively small country, there's not a ton of natural resources, nor really friendly terrains. There's a lot of like really rocky mountains and stuff like that that are difficult to live on. So there's not a ton of livable space in Japan. So the fact that their population is already so large, sort of they've reached that sort of carrying capacity limit of the amount of people that can live in Japan. There's a lot of also cultural things that sort of happen there. But essentially, what that means is that the population of Japan has sort of leveled out at about 130 million. And in some years, it's actually sort of decreased rather than increased. Okay. So, what does our logistic growth model predict that the population should be? So, A, what does the logistic growth model predict that the population will be in 2018? Well, this is a model that is in years since 1960. So we're looking for P of 58, which would be 130 divided by 1 plus 0.392 e to the negative 0.044 times 58. And when we plug that into a calculator, we get we get 126.15 million. The actual population of Japan in 2018 is about 126.4 million. So this model ends up being pretty accurate for that day as well. Okay. And in fact, if we actually take a look at this graph here, um, this is what this graph looks like, the logistic growth graph here. You can see it has this exponential growth before the date here, but after 1960, we're seeing this sort of increasing to a limit type thing here. All right. In 1980, the population, according to this model, would be 103.8. The actual population in 1980 was 103.7. Um, so this model is accurate for that 1980 date and also takes into consideration that they're reaching this carrying capacity, and so is also accurate for this date here. If we had just done an exponential model, we should expect to see this increase and sort of have a sort of be curving upwards rather than curving downwards like this, which means that an exponential growth model might have predicted that the population of Japan in 2018 would be up here around 200 million. But in reality, that's not true. There's that limiting factor that says in 2018, the population is actually like 126 million. Let's see here. It's about 8:46. So let's see here. Let's go ahead and really quickly. Are there any questions about the logistic growth model? I'm not going to ask you to do too much super sophisticated. Actually, let's do a part B to this real quick. Let's do B. When does the logistic model predict that the population of Japan will pass 120 million? So let's just do an example of solving an logistic model for T, because that's a little tricky and it's definitely worth looking at. So basically what this is saying is this is saying P of T is equal to 120, or 120 is equal to 130 divided by 1 plus 0.392 e to the negative 0.4044 t. Okay. So not only is our variable in an exponent, it's in an exponent in the denominator of this fraction. So first things first, I want to get this exponential part on its own. I'm going to multiply both sides by the denominator of this fraction here. I'm going to multiply both sides by 1 plus 0.0392 e to the negative 0.044 t. And we're going to end up with 120 times 1 plus 0.0392 e to the negative 0.044 t is equal to 130. Next, we can distribute this 120. We get 120 plus, real quick, whoop, that was 20 times 0.392 is 47.04 e to the negative 0.044 t is equal to 130. And then we can subtract 120 from both sides. So 47.04 e to the negative 0.044 t is equal to 10. And then we can divide both sides by 47.04. So e to the negative 0.044 t is equal to 10 divided by 47.04. And now we can apply a natural log to both sides. So negative 0.044 t is equal to the natural log of 10 over 47.04. And then we're dividing both sides by negative 0.044t to get that t is equal to the natural log of 10 over 47.04, all divided by negative 0.044. So we can go ahead and plug that into our calculator. ln of 10 divided by 47.04, all divided by negative 0.044, tells us that t is approximately equal to 35.2. So the logistic model suggests that the population of Japan passes 120 million in 1996. I want to say that Japan had a pretty big population boom in the 1990s, and that might not be 100% accurate, but that's what our model says. So, all right. Unless there are any other questions, I want to do one more quick example on exponential decay, just so that you guys have seen an exponential decay model. It's pretty much the same exact thing as those exponential growth models we started with today, except your exponent will be negative. But I just want to take a look at one real quick. So, after 500 years, a sample of radium 226 has decayed to 80.4% of its original mass. What is the half-life of radium 226? So here we're going to use the model A of t, the amount left in terms of time, is equal to CE to the KT. Okay? And we're going to assume that C is equal to 1. Or better yet, let's do 100 so that the percentages work out really, really nicely. Okay? So we're going to assume that C is 100. So that means that after 500 years, A of 500, that'll be equal to 80.4. If there were 100 grams to begin with, 80.4% of 100 is just 80.4, right? Which is equal to 100 e to the kt, or k times 500. We can divide both sides by 100 to get 80.4 over 100 is equal to e to the 500k, or 0.804 is equal to e to the 500k. And then we can take a logarithm of both sides. ln of 0.804 is equal to 500k. And then we can divide both sides by 500 to get k is equal to ln of 0.804 over 500. So that's ln of 0.804 divided by 500. So we end up with negative 0.0 0.00436 as um, our number here. Okay. And then we want to know what the half-life is. So we want to know at what time. So our model is A of t is equal to 100 e to the negative 0.000436 t. So we want to know when 50% of that remains, when half of it remains. That's what half-life means. Okay, so we want to know when this is equal to 50. So the first thing we should do here is to divide by 100. So we get 1/2 is equal to e to the negative 0.000436 t. And then, just like we did before, every single time we've tried to pull something out, once we've isolated our exponential expression, we're going to apply a natural logarithm to both sides. So ln of 1/2 is equal to negative 0.000436 t. And then we need to just divide both sides by negative 0.000436 to get that t is equal to ln of 1 over 2 divided by negative 0.000436. And we'll plug that into our calculator. Ln of 0.5 divided by negative 0.000436. And that gives our answer of about 1589.8. So the half-life of radium 226 is 15.89, or sorry, 1589.8 years. And that's exponential decay. It's the math is all identical to exponential growth. It's just that exponential decay, you end up with a negative k value. Everything else will work out exactly the same way. You're solving them in exactly the same way. You're building the function exactly the same way. Think of it like, so sometimes you have lines with a positive slope, sometimes you have lines with a negative slope. And when you have there's not really a difference between a line with a positive slope and a negative slope. In the same way, there's not truly a difference between a line with or an exponential growth function and an exponential decay function. It's just whether or not that k value that multiplies the t or the x or whatever is in the exponent is positive or negative. Okay. I think I'm going to leave it there. Does anybody have any questions before I let you guys go? So as usual, I'm going to post a practice sheet with an answer key. You guys can feel free to take a look at that. I will. There's also a homework assignment that's due on Thursday. Our exam will be on Thursday, and it'll be due the following Tuesday. It'll be an open note exam. So next class, I'll hold a short review session, and then I will hand out the exams and explain how the exam will work. Okay? Okay. I will post stuff and let you guys go.